Hello and welcome to Measurements with the Gamma Scout in a nutshell. In the following episodes, we aim to illustrate the versatile applications of this compact device, which is utilized across multiple areas, including research, industry, and personal use. Join us as we explore how this tool enables the straightforward and accurate detection of ionizing radiation, making it an indispensable asset in diverse settings. Today, we are diving into some key questions. Where does ionizing radiation occur? Why is it called ionizing radiation? And most importantly, how does the Gamma Scout detect it? Stay tuned for the answers. When discussing ionizing radiation, the first idea for many is that this radiation originates from man-made sources. We think of materials generated in the production of nuclear energy, or radiopharmaceuticals used in nuclear medicine. In addition, also X-rays, which many of us have encountered before, are ionizing radiation. Many, however, tend to overlook the ionizing radiation emerging from natural sources, which surround us at all times. This radiation is released when unstable atomic nuclei undergo radioactive decay. Such decay processes are happening permanently all around us, but we often don't notice them. For instance, traces of uranium, a radioactive element crucial for energy generation in power plants, may be found in common rocks like granite and in coal. Similarly, thorium, which is even more abundant on Earth than uranium, releases ionizing radiation as it undergoes radioactive decay. In addition, ionizing radiation also reaches us from the depths of outer space and the sun. However, what are the specific interactions of this radiation? Which effects does it cause in its environment? As the name implies, ionizing radiation, such as alpha, beta, and gamma radiation, is able to ionize molecules and atoms. In other words, it is able to break chemical bonds and transform individual particles into positively and negatively charged fragments. The Gamma Scout uses this ionizing property of the radiation to detect it and measure its exact quantities. Mounted inside the Gamma Scout, there is a Geiger-Müller tube, which is shown here schematically. In its center, there is a wire functioning as an electrode. A voltage of several hundred volts is applied between this electrode wire, having positive charge, and the metal body of the tube. The center electrode thus acts as an anode, attracting negatively charged particles towards it. Contained within the volume of the tube is a gas mixture, consisting mainly of the noble gas argon. The Gamma Scout is utilizing a special type of GM tube with an end window which is built from a low-density material, for example mica, which is permeable for alpha and most beta particles. If an alpha or beta particle passes through the window, it starts interacting with the gas, promptly ionizing its particles. Gamma rays need to interact with more dense materials, like the body of the tube. The resulting positively charged fragments are subsequently accelerated towards the tube body. Negatively charged fragments, mainly electrons, are accelerated towards the anode wire. The closer the electron approaches the wire, the stronger it is accelerated. These fast electrons have enough energy to produce further ionization in the gas, resulting in an electron cascade propagating through the entire tube. These avalanches need to be controlled by a quench gas. At the end of this process, all generated charges are collected by the anode wire and the cathode body, producing a flow of charges. This electric current is conducted through the counting instrumentation of the device. The height of this electric current pulse is always the same, irrespective of the particle which has produced it and its energy. Therefore, a GM tube cannot differentiate the type nor the energy of the radiation. The entire chain of events, starting from entry of the radiation and ending in the generation and detection of a current passing through the circuitry, takes place in about 100 microseconds. During this dead time, the tube is unable to register and count any further ionizations. Hence, this time is called dead time. To distinguish different types of ionizing radiation, we need to make use of the different penetrative abilities of alpha, beta, and gamma radiation respectively. We will demonstrate this in the videos focusing on the measurement of each radiation type. At this point, we briefly want to mention that, with the help of the gray lever on the Gamma Scout, various shields can be inserted in front of the GM tube. To detect all three types of radiation simultaneously, the shield can be omitted completely. To measure beta and gamma radiation, a thin aluminum foil is chosen to be placed in front of the GM tube. For selective measurement of gamma radiation, a thicker aluminum plate is employed. And on that note, we bid farewell and sincerely thank you for watching. If you've enjoyed this video, please give it a thumbs up and subscribe to our channel to stay tuned for all our future content. If you have any questions or suggestions, feel free to leave a comment below. We look forward to seeing you again next time. Until then, take care and see you soon.